In the outer solar system, far from the Sun, there are worlds that look frozen and dead on the surface. But beneath that ice, some of them may be hiding oceans deeper than any on Earth. And inside those oceans, the conditions for life may already exist. For most of the history of planetary science, the search for life elsewhere followed a straightforward idea. You looked for a rocky planet in the right orbit, at the right distance from its star, where sunlight could keep water liquid on the surface. That thinking made Mars the obvious target, and for good reason. But starting in the late 1970s, something unexpected began to emerge from the data coming back from the outer planets. Moons, not planets, were showing signs of internal heat and possibly liquid water. And they were doing it in places where sunlight is barely a fraction of what reaches Earth. The key mechanism is tidal heating. When a moon orbits a massive planet, the gravitational pull flexes the moon's interior as it moves through its orbit. Over millions and billions of years, the repeated squeezing generates enough heat to melt ice from the inside out. The result is a subsurface ocean, sealed beneath a shell of ice, sometimes kilometers thick, kept warm not by the sun but by gravity itself. That single idea changed how scientists think about habitability. You do not need a warm surface. You do not need a thick atmosphere. You need an energy source, liquid water, and the right chemistry. And it turns out that several moons in the outer solar system may have all three. The clearest example is Europa. It is one of Jupiter's four large Galilean moons, and it has been on scientists' shortlist for decades. Europa's surface is one of the smoothest in the solar system, crisscrossed by fractures and ridges but almost completely free of large craters. That lack of craters tells us the surface is geologically young, possibly between 30 and 180 million years old, which means something is actively resurfacing it. The real breakthrough came from the Galileo spacecraft, which orbited Jupiter from 1995 to 2003. Galileo carried a magnetometer, and as it flew past Europa, it detected something striking. Europa does not have a permanent magnetic field of its own. But as Jupiter's powerful magnetic field sweeps past the Moon, something beneath the ice generates an induced electrical response. The best explanation is a layer of salty liquid water, conductive enough to produce the signal Galileo measured. That is not a guess based on surface features. It is a physical measurement of a magnetic effect whose strongest interpretation points to an ocean hidden below. Current models suggest Europa's ice shell may be on the order of 15 to 25 kilometers thick on average, sitting on top of a global ocean that could hold more water than all of Earth's oceans combined. And because that ocean is likely in direct contact with a rocky mantle at the bottom, hydrothermal vents on the seafloor could provide chemical energy, much like the deep ocean vents on Earth that support thriving ecosystems entirely independent of sunlight. The surface itself holds clues. So-called chaos terrain, where blocks of ice appear to have broken apart, drifted, and refrozen in new positions, suggests that warm water or convecting ice may have intruded from below. Europa also shows evidence of possible water plumes erupting through the ice, though confirming those plumes has proved difficult from a distance. If they are real, they would give future missions a way to sample the ocean chemistry without ever drilling through the shell. If Europa is the iconic candidate, Enceladus is the one that delivers the strongest chemical evidence so far. Enceladus is a small moon of Saturn, only about 500 kilometers across. But at its south pole, dramatic fractures called tiger stripes are venting plumes of water vapor and ice grains into space at hundreds of meters per second. These plumes are so substantial that they feed Saturn's E-ring. And because they are spraying material from a subsurface ocean directly outward, scientists do not have to guess what is in that ocean. They can measure it. The Cassini spacecraft flew through these plumes multiple times, and what it found was remarkable. The ocean inside Enceladus contains the 6 elements that life on Earth depends on most: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Phosphorus was the last to be confirmed. Analysis published in 2023 showed that ice grains from Enceladus contained sodium phosphates in concentrations at least 100 times higher than Earth's oceans. Phosphorus is essential for DNA, cell membranes, and the energy molecules that power living cells. Finding it there means that Enceladus has all the basic chemical ingredients we associate with biology. The ocean also appears to be alkaline, and heat from the Moon's interior likely drives hydrothermal reactions between the water and the rocky core, a process that could supply energy for any microorganisms that might exist. Recent work published in 2025 adds another detail. Cassini's infrared measurements show that Enceladus's north pole, previously assumed to be geologically quiet, is measurably warmer than passive thermal models predict. Heat is leaking from the interior across the entire Moon, which suggests the ocean has been stable for a long time. Stability matters, because life, if it were to emerge, would need time. So Europa and Enceladus are the headline cases. But the story has grown far beyond those two. Consider Titan, Saturn's largest moon and the only satellite in the solar system with a dense atmosphere. Titan has long been thought to hide a global water ocean beneath a crust of water ice and organic material. But a reanalysis of Cassini's radio science data published in 2025 has complicated that picture. The new model suggests that Titan's interior may not be a clean, well-defined ocean at all, but rather a high-viscosity slush, a mixture of ice and water where ice crystals grind against each other and generate friction. In this model, the only true liquid water might exist in isolated pockets near the rocky core, possibly at temperatures warm enough to sustain complex chemistry. This is not a step backward for habitability. It is a refinement. If water pockets near Titan's core can cycle nutrients through the slushy layers toward the surface, they could create localized environments where prebiotic reactions happen. Titan's surface already has complex organic chemistry going on in the open, driven by sunlight interacting with the thick nitrogen-methane atmosphere. The question is whether that surface chemistry ever mixed with liquid water, and for how long. The answer may come from Dragonfly, a NASA mission scheduled to launch in 2028 and arrive at Titan in 2034. Dragonfly is a nuclear-powered rotorcraft that will fly through Titan's atmosphere, taking advantage of the Moon's low gravity and dense air to cover far more ground than any rover could. Its primary target is Selk Crater, a site where an ancient impact may have briefly melted surface ice, allowing water to mix with the organic compounds already present. Dragonfly's mass spectrometer will search for amino acids, fatty acids, and other molecular signatures that could reveal how far chemistry has progressed toward something resembling life. Then there is Mimas, which might be the most surprising member of this list. Mimas is a moon of Saturn, famous for a single enormous impact crater called Herschel that gives it a striking resemblance to a certain fictional space station. For years, scientists treated Mimas as geologically dead, a battered block of ice with no signs of internal activity. But detailed analysis of its orbital wobble, its libration, has changed that view. The data suggests that Mimas is hiding a liquid layer beneath its surface. What makes this ocean unusual is its age. Current estimates suggest it may have formed only within the last 25 million years, which is extremely recent on geological timescales. That would explain why Mimas shows none of the surface fractures seen on Europa or Enceladus. The ice shell has not had enough time to crack in response to the ocean beneath it. Research from 2025 raises an even more dramatic possibility. As the ice shell thins from below, internal pressure could drop low enough to reach the triple point of water, where liquid can boil into vapor. This process might explain unusual crater shapes on the surface and suggests that Mimas is still actively evolving. If you widen the view beyond Saturn, the picture keeps expanding. In 2023, new interior modeling concluded that 4 of Uranus's 5 major moons, Ariel, Umbriel, Titania, and Oberon, likely contain internal oceans dozens of kilometers deep. These oceans are sustained not by tidal heating alone, but by a combination of leftover radiogenic heat from the Moon's rocky cores and the presence of chemical antifreezes like ammonia and chlorides dissolved in the water. Observations from the James Webb Space Telescope have revealed CO2-rich ice on the surfaces of these moons, particularly on Ariel, where material appears to have been deposited relatively recently. These findings are still indirect. No spacecraft has orbited Uranus since Voyager 2 flew past in 1986. But the models are strong enough that Ariel and Titania are now considered high-priority targets for a future Uranus orbiter mission. Even Triton, Neptune's largest moon, may belong to this family. Triton orbits Neptune in the wrong direction, retrograde, which is strong evidence that it was not formed alongside the planet but was captured from the Kuiper belt. It is one of the coldest objects in the solar system, yet it has active plumes of nitrogen shooting several kilometers into its thin atmosphere. For decades, the dominant theory held that these plumes were driven by sunlight, a kind of solid-state greenhouse effect where light penetrates translucent nitrogen ice and heats it from below. But newer models suggest that tidal heating, generated as Triton's orbit slowly circularized after capture, could sustain a long-lived subsurface ocean and drive the plumes from within. If that turns out to be correct, Triton would be a bridge between the icy moons of the giant planets and the distant dwarf planets of the Kuiper belt, including Pluto, which also shows evidence of internal water. Underlying all of this is a question that biology on Earth has already partly answered. How resilient can life be? Research on cold-loving microorganisms shows that some can grow at temperatures well below the freezing point of pure water. Studies of the yeast Rhodotorula frigidalcoholus under simulated ice-immune conditions reveal that these organisms can effectively pause their cell cycles and redirect resources toward DNA repair when conditions become harsh. This does not prove that life exists on Europa or Enceladus. But it does show that the temperature and pressure conditions inside an icy moon's ocean are not automatically fatal to biology as we understand it. All of which brings us to the decade ahead. 3 major missions are now en route or in development, each designed to probe these worlds and, in different ways, get closer to the oceans hidden inside them. The European Space Agency's JUICE spacecraft launched in 2023 and is currently making its way toward Jupiter. In August 2024, it performed an unprecedented double gravity assist, using both the Moon and Earth in a single maneuver to bend its trajectory. After a Venus flyby in 2025, it is on course to reach the Jupiter system and eventually enter orbit around Ganymede, the largest moon in the solar system. JUICE will study Ganymede's unique magnetic field and its layered interior, while also surveying Callisto and Europa during flybys. A 2024 reanalysis of Galileo's magnetic data has strengthened the case that Callisto, long dismissed as geologically inactive, also hides a salty ocean sealed beneath a thick ice shell and possibly in contact with a rocky core. NASA's Europa Clipper launched in October 2024. After a Mars gravity assist in early 2025, it is headed for the Jupiter system, where it will arrive in 2030. Rather than orbit Europa directly, which would expose the spacecraft to damaging radiation from Jupiter's magnetosphere, Clipper will orbit Jupiter itself and perform 49 close flybys of Europa, some as low as 25 kilometers above the surface. Its radar instrument will map the ice shell's internal structure and search for pockets of liquid water inside it. Its mass spectrometer will analyze any plume material it encounters. And its camera system will image the surface at a level of detail never achieved before. The mission is built around a single question: does Europa have the 3 ingredients, liquid water, chemical energy, and a stable environment, that life requires? And then there is Dragonfly, heading for Titan, the only one of these 3 missions that will actually touch down on a surface. Together, these spacecraft represent the most sustained scientific effort ever aimed at the ocean world question. The evidence gathered so far tells us this much. There are multiple moons in our solar system with subsurface oceans. Several of those oceans contain the basic chemical ingredients associated with life. At least a few appear to have been stable for long periods. And the icy shells above them may occasionally open, delivering material from below that we can study without ever landing. None of this proves that anything is alive beneath the ice. But it does mean that the question has moved from speculative to testable. For the first time, we have the tools and the targets to go look. If life exists anywhere nearby, we may not find it on a sunlit plain or in a warm, shallow sea. We may find it in black, pressurized water, under kilometers of ice, on a world that looks entirely dead from the outside. The outer solar system is not empty. It is waiting. And if you had to pick one icy moon as the best candidate to change everything, which would you choose?